Okay, I just realized I gave you this whole 25-minute explanation without recording it, but that means you don't have to watch as much stuff. Okay, so just, okay, we have 4 points. And these points will vary depending what your A, B, C, D, E, F, and G vectors are, or numbers. But everybody's going to have 4 points. These 4 points could be depicted by 4 points in the plane and the familiar picture. And what we want to do is we want to get the line y equals b plus ax that best fits these points. So ask, for a quiz, and people got this very quickly. What's the matrix A in the equation ax equals b? Because this is what we did last time. We're just kind of doing a synopsis of what we did last time, but we're doing it for 4 points rather than 3. Okay. So it's the ax equals b, where x equals ba is your target vector. X equals ba, where ba are the parameters of your straight line, the y-intercept and the slope of your straight line. And b is your target vector, which is a set of y coordinates. Okay. So the question then is, what's the rank of A? What are the dimensions of B and W? And what's the column space of A? Well, people got all or most of this very, very quickly. I think I commented that means that you're paying attention, staying on top of things, reviewing things and stuff, and something we don't always see. So you always set a high standard, and I'll try to live up to it. Okay. So we very quickly see that this is the matrix, and you can refer back to the previous class if you're not sure of this, but everybody seems to be sure of it. So I'm not going to belabor the point. Okay, now we have this matrix A in the equation. AX equals B now looks like A times your BA, BA being the parameters of your regression line, and this being your target vector. And commented that well, okay, so this is this form, and what we want to do is we want to find x that gets us as close as possible to this B vector, because that would give us the straight line that comes closest in some sense to our data points on the average. And what it really does is it minimizes, and I've got little arrows here indicating that this point here is a little bit below the line, it's this far below, this point's this far above. We did this last time. You got these distances of the points from the line. And what we want to do is minimize the average of those distances, and actually the average of those squared distances, again, for reasons we talked about previously. So that we want to minimize the difference between this matrix A times your BA, the AX, and the B. So we want to minimize the magnitude of AX minus B, but really the magnitude of AX minus B quantity squared. Okay, well, we got our vector spaces B and W. The dimensions of B and W are what? Well, A operates on B, takes us into W. It's very clear that these vectors had better be two-dimensional vectors. Okay, and of course they are. They're BAs. And the vectors over here are going to be four-dimensional vectors because, of course, this one, for example, lives over here. And if we multiply this matrix, we have to multiply it by a vector that has dimension 2, and we're going to get a vector of dimension 4 because we have 4 of those. Okay, so there's our situation. Now we do a picture here that label it not exactly randomly, but not all that well. Okay, we got our space B and our space W. B is two-dimensional. We think R2. W is four-dimensional. We think R4, because any two-dimensional space is isomorphic to R2, and any four-dimensional space is isomorphic to R4. The null space of A, we'll note, is the zero vector, because unless all these points are multiples of the vector, well, unless A, C, B, and E are all the same, in which case all these points would lie on a vertical line, and we'd already have our line. The rank of this matrix is going to be 2, because this vector is not going to, this column vector is not going to be a multiple of this column vector. And that makes null space of A 0. I commented that for any real world data that's done with great precision, this is never going to be expected to be, well, getting ahead of myself. Well, no meaningful real world data is going to have these numbers all the same. Okay, that's all there is to it. And unless they're all the same, you can see that the rank of this matrix is going to be 2 and the null space is going to be 0. Okay. The nullity that consists of 0 vector. Now, looking over here, we have R of A. That's what we call the range of A. That's the reason for R. There's a lot of ambiguity. You got an R here, you've got an R here, and you want to think row space when you see R of A. Row space, that's not what it is. It's a range of A. So we have the range of A over here. And there it is. We just depicted by a blob here because we're in 4-dimensional space. We might as well. We have our vector B. Okay, this vector over here. Now, if this vector is in the range of A, we're done because all these points do lie on a straight line. You think about why that's. Now, I don't know what I didn't really label this. Okay. But my point here is when our root vectors are orthogonal to R of A, well, that's what we have. I don't have a good place to draw my arrows. I just have to draw it here. Vectors out here are all orthogonal to R of A. That's pretty easy to establish. And we'll kind of leave that detail right now because we want to get the overall picture. But we'll accept that these vectors are all orthogonal to these. And again, that's easy to show. At this point, I think I went over here and said, okay, well, let's go back to the picture we had when we had 3 data points. With 3 data points, this would have been R3 rather than R4. So we have these 2 vectors here. These 2 vectors would be our 2 columns of A, because the 2 columns of A are going to map over into this, and they're going to form a basis for the column space, unless, well, they do form a basis for the column space. Okay. And that column space can kind of be depicted as a plane, and your B vector, the y coordinates, is here. And it projects down into this plane. Now, this is just to relate the picture we drew last time to what we're doing now. A simplified picture of this, I think your book uses the symbol S for the column space of A. I would have just called it R of A, maybe. All right. And the picture looks much like this. You've got your B vector here. And what you do is you project your B vector down into the column space. Okay, well, the B vector projects in your column space, giving you an AX for some X. Because this vector is in the column space. Column space consists of all the images of these vectors that occur over in W. Okay, so here we're in W, we got our B vector, we got our AX vector. Okay, so I just wrote, projection of B into the column space is the closest vector in the column space to B. it's intuitive if you think vectors and planes. It's easy to prove more generally, and you want to be sure you digest that proof. This vector is b minus ax. The picture, you know, ax plus this vector equals b, so this vector is b minus ax. We come back over here. Here's our b vector. Here's a projection of b into range of A. Okay. The vector from here to here is orthogonal to the column space or range of A. Okay. This vector is orthogonal, meaning that it's not in the column space, it's orthogonal to the column space. So it's going to be the, well, okay, so this vector is orthogonal to the column space. Okay, so the question is, what does this vector come from over here? If we can find what this vector comes from, then we've got our desired x. We've got the x that solves this equation. Well, pull this vector back here. We just multiply this vector by A transpose. It's going to give us the zero vector. It's going to give us what? This vector is not in the column space. If it was in the column space, then okay, now I'm losing my thread here. We'll just accept. Okay, A transpose times this has to equal to zero vector. I'll explain that again in a minute. The point now is then that we have this equation that A transpose times this vector has to equal to zero vector. And that leads you to the conclusion that A transpose times A, well, we just rearrange this equation. A transpose times AX minus A transpose times B equals zero. And then we just use matrix algebra to move this over on this side. We get A transpose times AX equals A transpose times B. And now you have the problem you've been working on. Okay, and it looks like you just wrapped it up. Okay. This is easy to calculate. A transpose B, well, you've got the A matrix. You wrote the thing down. You know what your B matrix is, you know, your B vector, you got that. So you can do this. Okay. And what's A transpose times? Well, you got your A matrix. A transpose times A transpose is going to be a 2x4 matrix, which you multiply by a 4x2 matrix. And all you have two rows multiplying two columns is going to give you a 2x2 matrix. So this is going to be a 2x2 matrix that you multiply by x to get something you can calculate, and then you solve this equation. Now, the thing I didn't tell you that occurred to you is that this matrix is invertible. So you find the inverse of this matrix, multiply it by what you calculated here, and now you've got your B and your A, so you've got your regression line. Okay? So there we have it. And I'm sorry, I got sidetracked here. If I'm not developing it, then this is a reason I don't work from notes. Okay? I can't keep my train of thought if I'm doing something that's already been done. Okay, just the way my feeble brain works. And I think I explained it perfectly well when I wrote it out, but now I'm trying to imitate what I did earlier, which is a bad way to proceed. Okay, you want to reason it out step by step. So take that as a lesson. If your mind works anything like mine, and you know, you have my sympathy if it does. But I'll come back to that in a minute. Let's see what you got. And the camera zoomed way back at some point, but it fortunately stayed in focus. So I don't have to do this again. So let's just zoom it back in. I wish the thing would behave, but it won't. Okay, so hopefully that was all visible on the video. Okay, now I was trying to follow my train of thought when I did this instead of developing my own train of thought as I went on. Okay, and of course I just totally neglected this statement up here. Okay, now reason for this statement we can address, but think about why this is true, because I think what I said when I did this was you want to think through why this is true, because it just involves the meaning of the transpose and how it works over here. Okay, it's pretty obvious if you think it through and write it out. So I'm not going to take time to do that right now because we need to move on to complex vector spaces. Okay, so if you have a question on that, we'll come back to it. We pretty much addressed it last time, but not completely. Okay, now your text doesn't develop this in the context of planes and lines, orthogonal and stuff. But remember that orthogonal to a plane, you have a line in 3 space. If you got a plane in 3 space, perpendicular to the line is one particular direction. Okay, so it's as though in 3-dimensional space, you've got the column space, which in this case was depicted by a plane. And then you've got the space perpendicular to that, which might be in the direction of this line. Okay. So this is the maybe I'll never learn to write R back with just a simple R. So this is the line through the origin perpendicular to this plane. Remember also, when you're thinking of lines and planes in 3 space, for example, you're talking about lines and planes that go through the origin because all your vectors are rooted at the origin, okay? So these column vectors here are rooted at the origin, so you're seeing a plane through the origin, not an affine plane, which would be above or below the origin, okay? And we're not going to talk too much about affine planes and affine spaces. But basically an affine space, you just take this space, which you visualize as a plane, and then you add some vector to it, which moves the origin and every other point, whatever the displacement of that vector is, okay? Okay, well, there's more to it, but we're not getting into it. Okay, so your space perpendicular to this in 3 dimensions is just a line through the origin. In higher dimensions, you think of a plane here and another plane that's totally perpendicular to this one. Well, you can't visualize 2 planes that are perpendicular to one another, okay? You can visualize a line perpendicular to a plane, but 2 perpendicular planes doesn't occur in 3 space. And since we live in 3 space and all our experiences in 3 space, we have no idea what that would actually look like in 4 space. Actually, we do projections and stuff, we get some kind of intuition, but we still don't have a picture. Okay, well, that's all I want to say right now. I want to go on to the idea of a complex vector space. I'm assuming you're okay with complex numbers. Stuff I ask you to digest for today is it's pretty straightforward, and I don't have my copy of it. Okay, well, I need to look for it to do this. Okay, vector space consists of vectors composed by complex numbers. Okay, so for example, that would be a two-dimensional vector composed of complex numbers. Instead of R2, we'll call this C2. Okay. Now, if you have Cn, that just means you got n components, right? So it's just like Rn, except now it's Cn. Okay. And your scalars. Are complex numbers. And you know what? We're going to divide this into two videos. So I'm going to stop this one and pick it up in a second video.